Hello, this is the fourth video of the Hyperbolic Functions Series 2 on inverse hyperbolic functions for OCR Pure Core Further Mathematics, and it covers integration using hyperbolic substitutions. Using a substitution can be a good way to integrate an expression that would otherwise be outside the range of our experience. For example, for a function involving the square root of x squared minus a squared, the substitution x equals a cos u can be useful. Other videos consider using circular trig functions as substitutions in detail, but here we will only consider an example using hyperbolic functions. In this example, using a substitution of the form x equals a cos u, we are asked to find the integral of the square root of x squared minus 9 dx. Note that we have listed identities for hyperbolic functions that you will see are very similar to those you have been used to for the circular trig functions. Note that if we use this substitution x equals 3 cos u, we will be able to take a 3 outside the square root when we switch variables. So we have the integral of square root of x squared minus 9 dx, and if we use x equals 3 cos u, then we find that dx by du will equal 3 sin u. So replacing the x's by u's would give us the square root of 9 cos squared u minus 9 dx by du, which is 3 sin u, and then du. Using the identity that cos squared u minus sin squared u equals 1 means that we can take that 3 out of the square root and say that that's under the square root would be cos squared u minus 1, and we'll replace that by sin u. We're then multiplying again by another 3, so we'll make that a 9, and by another sin u, so we'll make that sin squared u du. In order to integrate for sin squared u, we can use this identity here, that cos to u equals 2 sin squared u plus 1. We'll move on to the next slide to give us more room to show this. So replacing that 9 sin squared u with using that identity would give us 9 over 2 cos 2u minus 1 du. And we know how to integrate that to give us 9 over 2, a half, because it's cos 2u, sin 2u, and then the minus 1 integrates to just being minus u, and not forgetting the constant of integration. However, we're not finished yet. We need to move back to the x variable. So, having used this identity already, this integral of cos x giving us sin x, we can now use this next identity, which looks very similar to the circular trig double angle formula. So this gives us 9 over 2, and then the half sin 2u can be replaced by cos u sin u. We've still got that minus u, and we've still got the plus c. So we remember that x equaled 3 cos u, and therefore that u must be cos to the minus 1 of x over 3. Using this identity here, we can see that if we want to replace sin u, this would be the square root of cos squared u minus 1. Or if we replace that with the x, that would be x squared over 9 minus 1. And we can, by rearranging and taking out a factor of a third, say that that's a third of the square root of x squared minus 9. So with that additional information, we can move on further. So as you can see, we have replaced the cos u by the x over 3, the sin u with this factor x squared over 9 minus 1 square rooted, and then the u term with the cos to the minus 1 x over 3. Sorting all that out gives us a result of x over 2 square root of x squared minus 9 minus 9 over 2 cos to the minus 1 x over 3 plus c. If we wish to, we could then replace the cos to the minus 1 using the logarithmic form. And this component would then become minus 9 over 2, a natural log of x over 3 plus a third of the square root of x squared minus 9. And obviously again not forgetting that plus c. So what may have looked like a reasonably straightforward integral, being just the integral of the square root of x squared minus 9, actually ends up having some interesting terms in the solution. But you can see that they all do relate to that square root of x squared minus 9. And the hyperbolic function was a very useful substitution. This is the last video of the hyperbolic function series 2 on inverse hyperbolic functions.